Over the past year, our final year project team has been developing an internal gear hub for Monash Human Power. Monash Human Power is an engineering student team here at Monash looking to break the human-powered land speed record. The international competition we compete in is held in Battle Mountain in Nevada in America, where we raced our most recent human-powered vehicle, Billy, reaching 116.39 kilometers per hour, making it the fastest bike in Australia. From here, we're chasing the overall human-powered land speed record of 144 kilometers per hour, and so we need to ensure that our drivetrain is reliable, compact, and efficient. This project set out to investigate whether the use of planetary gears would be effective in creating a compact but still efficient drivetrain. Planetary gears could reduce the required number of sprockets, but we still needed to provide the gear ratios for the rider to be able to hit those record speeds. It also needed to be efficient at the high speeds, and so therefore needed to be efficient at the highest gear ratios.
This hub concept is our answer to the design problem presented by MHP at the start of the year. The really exciting part about this hub is that the only purchased components are the planetary gears and the bearings, and the rest of the components were manufactured in-house by our team. The hub is key to allowing our riders to pedal up to 120 kilometers an hour and maintain a comfortable cadence while doing so.
Our gear hub requires two selectable output speeds. The high speed is direct drive, which is the most efficient gear because there's no moving parts on the inside of the hub while it's in motion. This direct drive gear means that when the sprocket is rotating, the wheel will revolve exactly once for every revolution of the drive sprocket. Our bike goes really fast, and in order for the rider to pedal while the bike's going at those speeds, we need a really big gear ratio. But the bike's not always going at these speeds. As the rider accelerates, we need a much easier gear in order to get up to that speed. And that's why we need a reducing gear ratio in our gear hub. Our lower gear is a 60% reduction, meaning that for every rotation of the sprocket, the wheel will rotate 60% of a revolution. With the two output speeds that our hub has, combined with the 4 speeds of the cassette, our drivetrain has a total of 8 speeds. So the way that we achieve the reducing gear ratio is using a thing called a planetary gear set. A planetary gear set has 3 components: the sun gear, several planet gears, and a ring gear. These gears can be utilized in several ways, but in this case, the sun gear is fixed to the axle, the ring gear is connected to the drive sprocket, and the planets are connected to the hub body, which in turn drives the rim of the wheel. For every rotation of the ring gear, the planet gears rotate a shorter distance, which gives us our reducing gear ratio. Selecting the right gear sizes meant we had to balance numerous factors, including getting the gears to mesh correctly, minimizing the size and the weight of the hub, and most importantly, making sure that the gears wouldn't fail under the large loads that the rider puts them through while riding. Having a reducing gear ratio at all was a challenge, but the other half of the battle was being able to shift between the direct drive and the reducing gear ratio. This was especially hard for us because we wanted to maximize the efficiency in the direct drive gear, which means entirely disconnecting from the input and the output of the planetary gear system while in direct drive. The solution we settled on uses 3 ratchet mechanisms, which are devices which transfer torque in just one direction. They're the same things you find in like your ratchet wrench or your ratchet straps. 2 of these ratchets use to direct the torque from the rider to either the hub body or to the planetary gear system. Exactly one of these is disabled at a time, so the rider's power is going to exactly one of them. A 3rd ratchet connects the output of the planetary gear system to the hub body, but only engages if the hub body isn't already being driven. This was likely the part of the hub that we spent the most time designing, as the functionality of it determines both the efficiency of the hub and also the reliability of the shifting. It was the single mechanism that caused us to redesign our hub concept several times before settling on the final design.
We used a Tormach slant lathe to machine the most concentric external and internal profiles for these parts. The most exciting was definitely the hub body, which turned out really well. Another machine used was the Tormach MX 1100 CNC mill. This mill allowed us to machine the complex planar profiles of the ratchet pawls amongst a host of other parts. A new process that we learned was broaching. To make a spline for directional power transfer, we managed to install a square edge piece of high-speed steel in the chuck of a manual mill, while the drive part was held in an indexing head. This indexing head allowed us to accurately broach at precise intervals while maintaining concentricity. The gears used in our design didn't perfectly conform to the gear specifications available on the market today. As a result, we needed to modify the dimensions, which was an incredibly delicate process. We actually damaged some of the planet gears in our first pass at altering the tooth engagement width. We found out that the gears were really sensitive to tooth geometry and surface imperfections, which meant that it wouldn't mesh. In the end, we were able to devise a system of soft collars and arbors to make sure that the machining processes weren't affecting the gears. Another challenge we encountered was organising machining timelines around the team's competition schedule. 2023 was Monash Human Power's first expedition to the United States to compete in Battle Mountain. We knew this was going to put a 3-week delay on progress at a critical time for the project timeline. In the end, we had to make some design simplifications and be very selective about the parts that we carried forward, so we could continue to meet deadlines and validate key technical requirements.
Our project was constrained by an extensive set of design requirements. The first performance criteria that we had was the mass of the hub. We designed the hub to minimize the mass. However, we know that there's still significant room for optimization even within the current design. The hub also needed to be able to withstand the significant loads of the road input, the system mass, the braking forces, as well as the torque input by the rider pedaling. We've been able to verify that the hub will withstand these loads using a variety of analysis techniques, including hand calculations and finite element analysis. Another key requirement for the hub is that it be entirely compatible with current chassis designs. Failure to meet this would have meant that our hub could not be used on current chassis designs without significant modification. This hub needs to be easily used by the rider and easily integrated into the power plans which we prescribed to them. By looking at the rider cadences from previous testing events, we were able to determine the intervals between the sprockets that we would require, as well as the size of the planetary gears which we would need. We figured out that a 0.6 reductions would be appropriate so that we could maintain a consistent increase in between the gears all the way from their 20 km/h start up to 120 km/h and faster. Energy efficiency was one of our top priorities when it came to this design, and particularly important was the efficiency of the high gear output, which is used during high speed and the high power section of the run plan. Our targets for this were above 99.7%, which we ensured by designing the higher output to be direct drive and not engage the planetary gears at all. This meant that fewer moving parts were necessary and there were fewer places to lose energy. The efficiency of the lower gear output is less critical, so the use of planetary gears could be justified. As of yet, we don't have the numbers for the efficiency, but we've been in discussions with a Monash-based lab, which has dynamometer facilities, and we will pursue this with the team's resources in the near future.
Critical next phase of this project is mounting the hub onto a dynamometer. We need to figure out the efficiency of the hub so that we can incorporate it into future drivetrain designs. And so this is something that we'll be actively pursuing within the team. Once we have some numbers of the hub in isolation and we're satisfied with the testing to that point, we will put the hub into a wheel and test it to verify the design requirements so that the team is getting what they envisaged. Obviously, one day we'd love to see this concept or a derivation of it used in competition at Battle Mountain. Even if some of this knowledge is useful to other members of the team or some of this manufacturing is passed down to the next generation, we'd call that a success. We're trying to break the world record of 144 km/h, and so every little bit helps.